Yeah, thank you, Jörn, for having me, of course, and thank you all for coming out on this wonderful Friday. I would like to talk to you guys about knowledge representation and reasoning in industrial robotics, and particularly about sort of the difference between the industrial domain and the service domains, what kind of reasoning and learning problems we face in industrial robotics, and also how we can tackle them using knowledge representation and reasoning. So my talk will have three parts. First, a small introduction to the domain of industrial robot programming, so from a programmer's perspective. Then I will show some application of knowledge representation and reasoning for symbolic program inference, so program synthesis. And then I would like to go a bit into neuro-symbolic programming and how we can use that approach to optimize program parameters for industrial robot programs. So to start off, industrial robotics, typically when people think about it, they think of processes like this, where you have very big and strong and fast robots moving difficult or heavy parts around or doing high precision things, and everything looks highly optimized and as if, okay, why do we even need knowledge representation and reasoning? Everything is already perfect anyway in this very shiny world of automation. Well, it sometimes helps to put things into historical perspective a bit and have a look at, where are we coming from. Actually, I think this is more of a continuum and less of a stage-wise process, but maybe around the 70s, we started to have industrial robots sort of being widespread in mostly also the automotive sector. And only later, maybe in the 2000s, we started to have the Industry 4.0 initiative and similar initiatives where we want to actually have interconnected cyber-physical systems in production. And then, of course, now we want to go in the area of what we call mass customization, which is basically using smart methods to do the sort of one-shot production or very individual, where each workpiece is essentially different. And you think, okay, well, based on what you saw earlier and based on what you think, okay, Tesla and Daimler and so on, they've got it figured out, right? We would expect most systems to be already at this stage. Well, it turns out actually that the distribution over, say, fanciness, right, for the production processes looks more like this. So there's a very fat tail of industrial production processes that are still very much in the traditional sort of 70s era pattern of automation where you have hard-coded robot programs written by hand that do sort of the same motion over and over and over again without having a sense of their environment, so as if they're blind, and really without having any sort of intelligence. And then by now the majority of processes are beginning to catch up or have sort of caught up into the Industry 4.0 era where you have data sort of collection mechanisms in place and you start to have sort of manual analysis of this vast amount of data you can collect in industrial processes, but still sort of not really a feedback back into the production, right? You gather all this data and you connect all these systems, but you don't really learn from that. And only a very, very, very narrow, very small tail on this side has actually gone into using any form of reasoning or any form of learning in order to optimize processes so that this sort of one-off production actually becomes feasible automatically. So the question is, what are the frontiers in industrial robotics that actually prevent this distribution from shifting farther and farther to the right? What is so hard? There must be something that prevents this sort of lump to move farther to the right. And well, it turns out that the sort of difficult kinds of industrial processes, you can see here some of them, right? So tight fitting of things at the sub-millimeter scale that involve contacts and friction. That's where a lot of things can go wrong. Also, the sort of unstructured environments where things are lying around in bins and have to be picked up, or flexible objects, deformable objects that need to be joined. I mean, I guess anyone who's ever built their own computer knows how annoying these ribbon cables are to manipulate, and we can do that with industrial robots. But the problem is that, well, we have noisy processes, we have tight manufacturing tolerances, we have wear and tear on our robots, and these all result in sub-symbolic optimization problems at very small scales that are quite nasty. Also, when we move into the sort of Industry 5.0 pattern, right, where we want to have this one-off production, small batch production, you constantly need to reprogram your robots, right? Before it was, okay, you program the robot once and it produces this particular car model for the next 10 years and that's it. Well, today, actually, robots produce different things maybe every day, every hour, right? Maybe even every single time. So you need to have dynamic reconfiguration of your production system, and this is a very challenging problem. You also have high mixed, low volume production. I talked about this a bit, but this is the sort of pattern that started emerging when you start to have, these more flexible technologies for production that actually enable every single product to be different. And you have also more flexible production patterns in the sense that you have flexible factories where human and robots interact, where maybe autonomous vehicles, transport vehicles in factories also interact with robots. And there you also need to be much more adaptive than you used to be. And these are sort of the difficult problems in industrial robotics that we face, and where we think that knowledge representation and reasoning can actually help to solve them. But the thing is, not all is lost. We also have some assets that are kind of special to the industrial domain, and that's we have, to an extent, structured environments. Now that, we know a lot of our environments. They're typically planned beforehand just for this production task. We have CAD data, right? We have, even often the engineers have a ton of knowledge about the sort of production cells that the robots are operating in. But not always. So this is actually more of a semi-structured thing in many applications because, again, we have humans, we have noise, so we don't know everything about the environment. And we have structured task and domain knowledge, and this is what I will be expanding on most, that we actually know a lot about the domains in which we operate. And we actually also know a lot about the tasks that we have to do. For example, here, sort of screwing or inserting flexible workpieces. This has been done many times, and we can extract task knowledge from that. So what keeps us from crossing these frontiers now, right? I say, okay, we know a lot, we have difficult problems, but why can't we solve them? Well, we think at RTMinds that most industrial robots and the way they are programmed today is like programming robots with your hands behind your back, right? You have these very arcane program representations. Typically, robots are programmed in a textual way. You write a lot of arcane text in a manual way. You have no reasoning at runtime. You need all of these very high-paid, very rare robot programmers who have a lot of specialized knowledge about programming robots. And this simply does not scale. So, you spend hundreds of thousands of euros for one actually very simple production line just to have your robots programmed in this kind of fashion. And this is very much the still predominant way of programming robots. And I was a bit shocked when I entered the industry that this is still like that. And that's also part of my motivation of why I want to go into, or why I am going into knowledge representation and reasoning, because we can do so much better. Of course, it is getting better, and this is, for example, KUKA Sim Pro. You have these graphical ways of programming robots, and they do have structured program representations, so a bit more than raw text, that effectively use the robot's capabilities. However, you still don't have task-level programming, and they're still robot platform dependent. So I think we can do even better. Now, ROS Industrial came along, and ROS Industrial is awesome because it is much more modular, much more flexible. You can, again, make very complex architectures built around ROS Industrial. And the typical pattern is you always have, or often have, path planning sort of at the highest level, then low-level control, and then you go directly on the hardware. However, the problem is that we're still missing, in this kind of pattern, something sort of more abstract than path planning. So you still don't have, it's flexible and modular. It is also robot independent because you can have different robot backends, but you don't have concepts for task level programming that are sort of supplied and universal. And you don't have really a structured program representations that scale. And the core problem, if you want to get anything going in the industry, is you need to be compliant with certification mechanisms, for instance, and industry standards. Otherwise, nobody will adopt, in the real world, your amazing reasoning solutions. And here you have, often you want to use the low-level control provided by the robot manufacturer and not that provided by, for example, ROS Industrial. Or you need to be compliant with programming standards, like the Volkswagen standard or the BMW standards. And if you're not compliant with these standards, even suppliers of, for example, Volkswagen will not use your robot programs simply for that reason. So we can do even a bit better. And that's some of the motivation as to why Artimines exists. So primarily we're a software company. We write robot software for programming robots. That's a simplistic view. We also write software and develop software for sort of running robots. So it's a sort of also one-time environment a bit for analyzing and collecting data and doing optimizations with it. We also have a service branch where we help actual industrial companies get going with our solutions and make prototype production cells and sort of assist companies on the way to more flexible automation. And we are becoming an AI company, and this is, of course, also why I'm here, because we think that augmenting, the sub-symbolic AI, neural networks, and so on, with knowledge representation and reasoning techniques can actually deliver a huge benefit. So we have two products basically. The Artimines robot programming suite is the sort of IDE for industrial robots that we have developed. And we have Learn and Analytics for Robots, which is a runtime platform that runs next to your robot on maybe in the cloud and can collect and analyze data that comes in. And we have the full cycle from planning all the way to optimization and scaling is supported. I'm sorry, this slide is in German. And we standardize hardware, so you have one program representation and sort of one software stack for pretty much regardless of what kind of hardware you use in your robot cell. So the core sort of innovation as to why we think that, or how we think we can do better with robot programming is really focusing on the program representation. This is the core thing. We have a task model, and the idea is we represent robot program as a directed graph of parameterizable templates. This is in a way very similar to task graphs, in that the control flow, of course, goes from top to bottom, and you have motion perception, control flow logic, or elementary math operations in your graph, for example, and you can define your own primitives, and you can chain them and hierarchically combine them and this is very important for us, not just in an abstract mathematical way, but in an actual tangible, user-friendly way via drag and drop and so on. And the core idea is that we then compile this graph into native robot code. This is fundamentally different to, say, for example, what CRAM does, where the plan is essentially at runtime directly executed on the robot. We don't do this mostly for the certification and sort of safety reasons, right? So we compile native robot code. Customers, users of our software can have that code checked by their in-house compliance departments, right? We can make sure that our compiler backends are compatible with, say, a Volkswagen standard or an Audi standard and so on. So this is the core idea of what we do software-wise. And here again, the upshot here is, task-based robot programming and explicitly thinking about program representations can deliver a huge amount of value already without any reasoning. And now we come into the more juicy part of my talk, which is how can we use knowledge representation and reasoning to deliver value in industrial robotics. And if you think about many people are not familiar with how robots are programmed in the wild. So you always have, or often have, this sort of four-part step in order to get your robot actually doing something. This is you program it, then you have this commissioning phase where you bring software and hardware together in the cell. You have a ramp-up phase where you slowly start to increase the pace of production. You actually get the real work pieces in, and you dial in your system so that you meet the quality and, for example, also performance criteria, as we heard earlier. And then you, of course, have the operation phase, but there also you're not done because you continuously need to maintain and maybe reconfigure your hardware and software. And during all of these steps, you see there are manual processes. So humans have to initially create the program. They have to do offline simulation. They have to do hardware-software integration. They have to fine-tune parameters. They have to maintain maybe afterwards. So this is done right now by humans. But we see tremendous potential for sort of AI-based solutions to help and to assist during this process at every single step. For example, synthesizing programs up front is, of course, an extreme case, but a bit more simple is maybe refining existing programs that humans have written, optimizing parameters, and so on. So you may think, okay, well, we have identified all of these blue sort of opportunities for AI. why is this not done yet? And we see that actually, no, there's still an AI adoption gap in industrial robot programming. So even though industrial robots are ubiquitous and everywhere in very many production domains, we actually have a very slow industry uptake of AI. And we call this the AI adoption gap. So AI adoption is largely limited to perception. And this is because, well, the rest is really hard. So we have programs that must be of very high complexity. You see here, for example, very many different small cables must be inserted, and a robot program that does this is hundreds of thousands of lines long. You also have very heterogeneous execution environments. So here you see, for example, the typical robot production cell really looks something like this and has a lot of external components, a lot of PLCs, a lot of sensors, a lot of actors that are non-robots. Maybe humans run around in it. You also have simply the challenges of the real world, as you probably all know very well, that the real world physics often behave in a bit more complex way than you anticipate and model. And you need sensor-based real-time feedback always. And this makes also generating programs upfront, for example, very difficult. And you, of course, have the human in the loop. At every single step of the way, you need to make sure that humans can understand your programs, humans can modify your programs, right? And humans can certify your programs, for example. So this is why, AI adoption in industrial robotics is maybe not as far as we would like it to be. And this is the last thing, yes, very high trust requirements. If you have humans and robots working together, such as here, if you have a neural controller for your robot, you better make sure that he doesn't slap the human by accident when maybe there's a spike in sensor data or so. So, we want to bridge the AI adoption gap, and we think there are 3 ways to do it. The first is to really focus on the structured program representations. So, sort of going a bit away, at least temporarily, from the end-to-end paradigm. We have a black box system, traded on data, and hope for the best, but instead leverage structured program representations that are modular, that are intelligible, that are interoperable. And we want to use structured knowledge representations like knowledge graphs, ontologies, etc., because this way we can effectively reuse human expertise, existing planners, and we can generalize through reasoning, rather than hoping to generalize through model size and amount of data, which also both of these things are a bit problematic in the industrial context. And if you have, so the third thing that we want to do is neurosymbolic programming. If you have a combination of the neural and the symbolic knowledge-based aspects, you can really get the best of both worlds and unlock maybe optimization problems or program synthesis problems that you couldn't do before. So jumping right in, application-wise, we have a look at the first bit, programming robots, and we want to do maybe knowledge representation and reasoning for program synthesis. Now, we tried to do this in a very first step by just using our hierarchical task knowledge and program representation to use hierarchical reinforcement learning. So what we did is an advanced critic algorithm, pretty standard in reinforcement learning. We did a hierarchical version of this and actually hand-coded this hierarchy of tasks. Essentially, sort of how the tasks can be decomposed. For example, the pick-and-place task consists of X, Y, and Z. And all pick-and-place tasks are fundamentally similar. So we have this sort of hierarchy going. We have a task-dependent reward. And what's kind of cool is we use NOROB to generate restrictions on the policy space. So sort of make restrictions as to which combinations, say, of primitives are permissible in a given, for a given task. And then we execute this, train it in simulation and execute it in the real world. And what we learned is what you would expect that, if you look at here, this is very important. At the X scale, you see that a linear policy that is not hierarchical takes forever to converge. It converges eventually, but it takes very long. Whereas a hierarchical policy converges, in maybe a factor of 10 less steps. So this was quite cool, but the problem was that it was still limited only to essentially fancier versions of pick-and-place tasks or combinations of pick-and-place tasks. But we could not scale this all the way to more complex tasks, mostly also that involve friction and contact in the real world. simply because we did not have a good simulator for this, and because the hardware requirements were surprisingly high. Even with a hierarchical policy, it took, at least on a regular, I don't know, fancy desktop GPU, way too long in order to converge. But this is an example for such a learned hierarchical policy, and you see, okay, we can already learn quite long robot programs in the end that are actually hierarchically decomposed, and this also helps humans to make sense of the program. You don't need to go all the way down to this very last primitive level. You can already sort of understand up here that this is pick and place, this is like pick, and this is maybe place, right? And the whole thing can be called stack and so on. So this was for the blocks word example. And this is how this works then. Always the advantage of using our software stack is that the simulation and the real world look very similar. This is because we have very good robot control structures that actually help us teach the robot to do what it should in the real world. But you will see a funny phenomenon now. Now this is a little suboptimal. And we thought teaching the robot how to, like, in a force-controlled way, maybe control this lid onto the bin, doing this with reinforcement learning, kind of blows up the problem. So we had a look at a different task that's a bit more complicated than pick and place. In this case, surface treatment. Here to the left, you see two examples of surface treatment. The one is sort of high power grinding of like steel surfaces. The other is deburring, for example. And we noticed that the domain of surface treatment can be, hierarchically split up into sub-concepts in a pretty intuitive way. And you have maybe adhesive and abrasive processes, and you have polishing, deburring, and sanding, and you have different tools like belt sanders and disc sanders that can do this. And it's very surprising how easy it is for humans to decompose such a domain, because I literally, I did this hierarchy on a train somewhere, not even thinking about it, and I knew, right, that okay, we have these kinds of things. So now we want to get this kind of domain expertise of humans actually also into our software systems to maybe do some, and this already looks kind of like an ontology, doesn't it? Reasoning over these kinds of the problem space, essentially, to generate then solutions that work in the real world. And what we also have, so we don't only have sort of an ontology of the domain, but we also have already very powerful tools for path planning over objects, and this helps us a lot. So this is already in our commercial software where we can generate paths given CAD models, and then that are overlaid with force constraints, so that you can say maybe push with 5 newtons against your surface while you grind, and always keep the angle of the orientation. You see a real-world example in a sec. Here, for example, you see how the orientation changes with the angle of the object. And now, what else do we need? Well, we need a real-world application use case, and we had a look at wind turbine refabrication. It turns out that even though we want to move to wind power, of course, we can't really recycle these turbine blades. They're huge and composite materials. It's very difficult to recycle. So what we thought we could do is we could refabricate them by grinding off the uppermost part. After about 10 years, they sort of degrade to the extent that the surface friction with the air becomes too big and they become inefficient. So we can grind them off and maybe refill them, repolish them, and reuse them. And we have a research project for this that's going on, and you see this is about 1/10 of such a blade. So it's actually quite huge. And this is the idea that we came up with. So this is the process. We sort of modeled the process. It's very simple. You have a look with a scanner maybe on your surface, classify it, the degree of degradation and maybe certain regions that you want to focus on. You select the tool for grinding, you do path planning, you actually do the sanding, maybe you do some error handling, and it goes on. And maybe if you detect that you have removed too much, you need to do some filling. And we thought, hey, there's actually a lot of chance to use NoRob, for example, and knowledge representation and reasoning to infer maybe things about what tools to select and how the path should be planned. And ultimately, but we haven't done this yet, we're actively still researching this, is how we can actually also use logic to do error handling and to help with the surface classification. But right now, what you will see is only basically these 2 steps. And what have we done? We have actually first written an ontology, in this case, for example, about the materials that we are likely to face. So you see and maybe aluminum, rubber, carbon, steel, wood, etc., and they all have different properties that are relevant for sanding. This is part of our domain knowledge. We also have process knowledge, and we have modeled this process that I showed in the other slide here using the Soma ontology actually as a sort of workflow. And we can also use this to make inferences at runtime for, say, error handling, and this is something that we will look into in the future. And having done this, now we have actually written little command line client, so this is still work in progress, hence the command line. And it, for example, asks you, hey, what kind of blade do you want to grind? And okay, this is the grinder you should use with this sort of rotational speed. And that it instantiates a robot program automatically with a very scaled down version of the blade, by the way. It asks you, how many millimeters do you want to remove? And you say 12. And it tells you what robot speed to set the robot at, and then it automatically generates a path that covers the workpiece, given the criteria that you want. In this case, because we're in the sanding domain, for example, we want to keep an orientation normal to the surface. And then it just simulates the program. And it does this in a loop, so afterwards it comes from the perception, how much have we actually removed, and you can do a close the control loop this way. And build quite nice interactive wizards this way that simplify the domain knowledge required to configure your system tremendously. This is one application of knowledge representation and reasoning. Another is in the space of retail robotics. So this is here at the University of Bremen in the Ilias project, which has just finished. And we have VR demonstrations of tasks in a supermarket domain, such as here, taking an object from this hanger. And the goal is to automatically infer a program that makes the robot do the exact same thing. We were in this lab a few days ago upstairs, and we actually tried this on a real robot. And how does this work? This is a bit complex overview diagram. I will just give a very high-level overview of this. We start with a VR demonstration. We interpret what actions at the event level correspond to the sensory data that we collect down here. We do a process which I called action interpretation, which basically maps from the action to the task. So one level of abstraction higher, from the event level to the semantic level. What is the meaning of this action? What task did this action do? And then we go down to again, of course, we have to go back down to the event level. We want to manifest things in the real world. So we go through a series of reasoning steps back down to actions and infer a robot program that actually can be executed in the real world, and this is fundamentally based on CRAM. So we use the CRAM cognitive architecture for several of the steps, almost all of the steps here. And this is a very big exercise in, again, systems engineering in many ways, because we combine all of these systems. So this is for one example of such a demonstration as a timeline, and you see that you have anonymous actions down here. So everything is just a physical action because we don't know yet what the human intended. We just know some event happened. And we can decompose this human demonstration and the states and so on that we see based on situation transitions. So when, for example, contacts happen and don't happen anymore, or when, and so on. And then we can say in Prolog, in our knowledge base, okay, we know that an action interprets to a task, so sort of generalizes to a task, if, well, it satisfies the precondition of a given task type, the runtime conditions, and the post conditions. And then we can maybe even infer some parameters of our task, given what we've seen. This is very simple. It's like in 5 lines we have solved the problem of program synthesis. No, we haven't, but this is sort of the power of these kinds of Prolog-based or rule-based systems, that you can write very concise solutions to your problems and hide everything behind these predicates, right? So what do we hide? Well, for example, we can say that the task of picking up, right? An action satisfies the preconditions of picking up if the object is grasped initially, and maybe the object is supported by something else, and then we can pick it up. Maybe runtime conditions are not important for picking up, and post conditions are the object is still grasped, but now it is not in contact with anything anymore, or it is not supported by anything anymore. That is not the gripper. So then we have picked it up successfully. And then we can use this rule base to infer a task sequence for all of our anonymous actions that we've seen. translate this one-to-one into a cram plan, and infer all the missing information, all the designators that have not been resolved yet, and we can resolve them at runtime by using perception, for example, or by using knowledge from our knowledge base. And then we can compile this into executable robot code and execute it on the real robot. And what happens? Well, this to the left is the simulation, for instance, and we use force control primitives, such as a little spiral search here to actually search for the hanger, and then we can do a force controlled insertion. And you see that in the real world, it looks very much similar to that. Now also notice that this is not sped up, because it's always a challenge to reduce the number of x, like you don't want to do 10x or 3x in your videos. Right? So we try to make it as fast as possible, and this is I'm very proud that this is reasonably tolerable with 1x. And come on. So I'm torturing you a bit here, but bear with me. The end is fast. There you go. Very nice. So, so if we want to go beyond symbolic representations and have a look at the rest of this, what can we do? We can do neurosymbolic robot programming to help with everything that comes after we have created our initial program. And our core idea here is the idea of differentiable shadow programs. This is always a fundamental question, is how you combine the symbolic and the subsymbolic. And you can either pull the symbolic via, say, embeddings, for example, into your neural architecture. This is one way to do it. But then you have the problem that you actually have to execute this neural architecture. We have decided, because in the industry, it is always good to keep the symbolic representation, because this is certifiable, executable, etc., and people can work with it. So under these constraints, we decided to go for the shadow approach. This is also a fundamental thing very similar to what people do for explainable neural systems, but the other way around. There they have symbolic shadows for neural networks. We have neural shadows for symbolic programs. So to explain this here, okay, we have our little symbolic robot program. Maybe this just a different view on this. It's still the same symbolic robot program. And what we can do is we can learn a differentiable model of this. What does this mean? We learn a sequence of neural components, maybe one for each primitive. And actually, I lied. It is not a purely neural component. It is also has a differentiable motion planner inside, which generates it's an algorithmic prior. It generates a prior trajectory given the inputs, x here, of our primitive. And so this way for a linear motion, it is simply linear motion, that's very simple, but for a spiral search, it is this spiral trajectory that is generated by a differentiable motion planner. And then we have a deep GRU behind it that adapts this prior trajectory given the sensory information that we see in the world. And for example, for the spiral search, it actually terminates the spiral, of course, when we found the hole and creates a little drop motion when whatever we want to insert actually dropped into the hole. And we can, of course, predict. So we can do the forward step, predict the expected trajectory, overall trajectory for our entire program down here. And we can, because it's differentiable, backpropagate. Not for learning, we can learn all of these individually. At runtime, we can freeze the weights and backpropagate just to optimize these inputs. And this way, we can put down here any loss function that we want, as long as it's differentiable. And we can generate optimal program parameters for our symbolic robot program here, for example. We can generate the optimal velocities and accelerations, or maybe even the optimal contact forces that we need, given the sensory data we observe in the world when trying this out. And this is, again, also the first example I want to tell you guys about. So contact motions are everywhere in the industry. Whenever you want to maybe fit two things together, you will have to establish contact. And depending on the materials, this is quite constrained. Here, for example, we don't want to exert 20 newtons on these little sensitive pins because they will bend. So what we have done is we have evaluated our shadow program architecture on these tasks. Here you see, like, we have a goal force of 5 newtons, say. We know that we want to be as quick as possible with our action, but never exceed 5 newtons. Actually, we want to hit exactly 5 newtons. And for a human, you would have to do a lot of trial and error to do this. What are the velocities and accelerations so that on this bendy PCB, you get 5 newtons of contact force? I have no idea. I would have to try this. And it takes a very long time for experienced robot programmers to do this kind of trial and error. And you see that, okay, well, the variance is very big. So for the same velocity and acceleration, you get a variance maybe 10 newtons at worst case and maybe 6 newtons or so in the best case. And using this gray data, after learning, our optimizer actually reliably hits 5 newtons, which is pretty cool. And here you see the video for this. So we collected training data by just hitting a PCB a few times. And then here you see if we set 5 newtons, we actually hit 5 newtons. If we say 6 newtons, well, we actually hit 6 newtons. So this is pretty cool, depending also. This way you can do very fast dynamic reconfiguration. If you have a different sort of, I don't know, part that you want to fit, and you know that it tolerates 6 newtons, throw that into your optimizer, and it will give you the robot program that hits 6 newtons. And we tried this for different materials and different goal forces. And yeah, it generalizes very well across also these kinds of different environments. We did the same thing for spiral search. I briefly explained spiral search before. What we found is that the same approach can also be used to adapt the parameters of such a spiral search to fit the underlying distribution of the holes, which is it's impossible for a human to do. You can't even see the distribution. This is sub-millimeter. So this is maybe 1 millimeter. It turns out that if you give a crappy loss function, our algorithm also returns a crappy result. Here, if you optimize only for cycle time, we were like, hey, we want to be as fast as possible. Well, it turns out our optimizer generates this little spiral, which covers only a fraction of the entire hole distribution. So you have to be careful about the loss functions, as with every optimized system, and actually include a measure of failure. So if you add the failure rate, or the probability of failure, and you want to maximize the probability of success or minimize the probability of failure, you generate a spiral that actually covers the entire distribution. Yeah. So one last thing that I want to show is if you have this in stochastic environments that actually shift over time. So if you have non-stationary environments, how can you do this? And we actually had a paper, or have a paper about this at IROS this year, where we built a heuristic-free, data-efficient optimizer that's robust against non-stationary process noise, and is still sort of this black box optimization algorithm that we have. For example, here you see a spike search or probe search, where you touch the surface repeatedly, initially in a grid until you hit a hole. And this is suboptimal. As you see, the grid has nothing to do with the spatial distribution of the holes over time. And of course, the optimized solution ideally is perfectly adapted to this distribution. So how do we do this? Actually, it's kind of a very similar approach. We start with our robot program. We train these forward models that I was talking about, so these shadow models of the skills, purely in simulation. So we know nothing about the distribution that we have actually in the real world. And then we take this, and we actually do transfer learning. So we have one test task. We only need 128 training examples, which is very little for an industrial use case. And we fine-tune the forward model on these 128 examples from our real world. We then run shadow program inversion, which is this where we use our shadow model to generate optimal parameters for a robot program, execute that, and because we want to do lifelong learning, because we don't know if the distributions shift over time, we can simply close the loop and use whatever we use in our production, we collect in our production cycle, back to fine-tune the forward model again and again and again. And it turns out that this is heuristic-free. We never make any assumption about any sort of Gaussian or distribution over holes or anything. You can use this for many processes. It is very data efficient. It is robust against non-stationary noise processes. In fact, it realizes its benefits only in non-stationary noise processes, and it is black box. And here you see such a non-stationary, or 2 examples for non-stationary noise processes with a spike search pattern. Initially, it started as a grid. Here in the drift process, you see that some points on the grid, because we have a regularizer that imposes actually that the optimizer is lazy. If it were too eager, all points would converge here. We don't want that. So it follows the kind of shifting distribution, and here you also see with Brownian motion which is much more chaotic than a drift. Well, it can kind of handle that. And always have at least one spike pose near the center of the distribution. So that's it for the technical content. I would like to highlight also our innovation lab at RTMinds, where we do all this research. We have started with this process about a year ago, trying to formalize the way in which we do corporate research and integrate with sort of public research projects, mostly. And of course, my awesome students who have helped a lot with this work. This is some examples of all the crazy other topics that we do that I have not covered in this talk. We are also busy building intelligent systems for minimally invasive robotic laparoscopy. So slightly different from the industrial case, but only slightly. And we have also dabbled in VR and intuitive programming interfaces using virtual reality, for instance. Yeah, we're members of several sort of committees and, of course, hope to extend these collaborations in the future. We are also, of course, loosely affiliated with EASE and yeah, hope to also get more active in the IEEE sort of environments. With this, I would like to conclude with the upshot of the talk, which is that the AI adoption gap in industrial robotics can be bridged, in our opinion, by three fundamental approaches. First, the systematic exploitation of structured knowledge program representations for robots, leverage composition, have intelligible programs, so intelligible AI, and leverage the interoperability that these program representations provide between robots. Use structured knowledge representations that allow us to take the benefits of existing sort of knowledge about domains such as surface treatment, and neurosymbolic programming as a way to bridge the world of reasoning with the world of subsymbolic data and experience. Thank you very much.
Mike.
Cool, that's extremely impressive, right? So one question, so I don't like kind of committees that put standards forward, right? And so I kind of prefer the approach when you actually show that something is useful, right? So in terms of ontologies, right? So you have an ontology that you have shown that you can automate some tasks that are relevant in industry, right? And I think in order to have impact, the question would also be, would RTMinds be willing to share these ontologies, or is it kind of so close to the kind of value of what RTMinds sells that I think it's critical, and only kind of your idea, not an official RTMinds statement to that, right? But
yeah, so we already publish the vast majority of our results. So nearly all of the stuff that you have seen in this presentation is either preprint or has been accepted to major conferences. And we also increasingly do even open code, so many of our algorithms and data structures can be found on GitHub also. But yes, and with respect to the ontologies, right? So I think many of the, for example, in the space of grinding or surface treatment, these kinds of ontologies, they are sufficiently general to provide enough benefit to other research endeavors because they encode domain knowledge, that it would make a lot of sense to share them, absolutely. With, for example, the sort of knowledge base about our movement primitives, for example, this would be, I think, not of that much use to others because, of course, we encode information about That's only specific to our program representation. But the fundamental reasoning algorithms behind that, and of course the ontologies, you have levels of ontologies, right? So maybe the very lowest level of ontology wouldn't be that beneficial. But the higher levels of ontology, of course, I'm absolutely for sharing them. Yes, absolutely.
Excellent. Thanks a lot.
Thank you. Sorry, you have to wait. Yeah, very impressive work. Thanks for the talk. You said you used neural shadowing for the merging of symbolic and sub-symbolic domains. You said you work with Karlsruhe, and Karlsruhe has very powerful formalisms for that, called probabilistic circuits, to merge these domains. Why are you not using them?
Well, that is mostly a question of the organization, like the way research is funded in Germany. So you have an incentive to, of course, work closely together with the research institutions that you collaborate with in public research projects. And we are actually looking forward and actively pursuing research projects with the KIT, for example, where these probabilistic, I think I know which parts of KIT you mean, where these are developed. And we are, of course, looking forward to expand the collaboration there. But as of right now, we don't have any projects with that department, so we haven't really used their solutions yet. But yes, we likely should. It's a very good point.
Okay, thanks.
I have a question about the demonstration learning that you showed with the automation in like the DM store or whatever. So you showed like where you like show it in VR, and then I don't know. You mentioned, for example, the spiraling motion, which I guess you cannot see in the VR, right? So you kind of have to add that knowledge afterwards. Like, so how is your process? Because I don't know. Like in the beginning, you have this trajectory, and then you said you segment it into different parts. And then I guess the semantic meaning has to come in somewhere, right?
Yes.
And then you have to have some specific knowledge, like the spiraling. So how much can you actually really learn, and how much do you have to add manually?
Yes, this was the fundamental question that makes this learning from demonstration from humans very difficult. And so I need this one here. So that's why we try to extract semantic meaning about the actions using knowledge representation and reasoning. So what did the user intend? What did the demonstrator intend at a task level? And we noticed that, okay, he intended an insertion task, maybe, or if we even know more, if we know that, for example, the thing that he inserts onto is a flexible or maybe a hook-shaped thing, right? We know that also, so it's like sort of insertion on a hook that the demonstrator is doing. And then when we map back down here to the task execution, we can have rules here in place where we say, okay, we know that a robot, in order to insert a thing onto a flexible hook, that is such a stochastic process because of all this flexibility that we need search for, in this case, the tip feature, right? We have feature abstraction, and we know that to insert something, we need to know about where the tip of the thing is that you want to insert on. And if there's uncertainty there, we have to search. So we add the search motion. If it's just maybe placing something into a container, we don't need search. But of course, if the container is very small, maybe we do. So we use, at this stage where we go from the task back down to the action, there we use reasoning to make the difference between what the human demonstrated and what the robot actually should do.
Thank you.
Oh, wow. Yeah, thanks for your insights. And you were always talking about verification and black boxing. I'm not pretty sure how that fits together, to be honest, because as soon as you learn on the fly, there's like no way that you're like ever going to achieve the same program again, the same parameters.
Yeah. So I talked about black box optimization for the optimizer for robot program parameters. But by that we mean you can use the same optimization algorithm for arbitrary robot program representations. So we have used that algorithm to optimize our own program representation. We have used it to optimize universal robot UR script programs, which are a bit more text-based. We have used that optimizer to optimize this dynamic movement primitives. So they also have parameters. So you can optimize any symbolic program presentation that has parameters using this optimizer. And that's what I mean by black box. However, the entire approach of optimizing the parameters of a symbolic program representation means that you know what these parameters mean. Because maybe it's the inputs for the spiral search. It's maybe the orientation of the spiral that you're optimizing, or the size of the spiral that you're optimizing. And because you know what the parameters that you optimize mean semantically, you can put checks in place that guarantee that certain safety-relevant criteria are always met. Right? For example, you can make a check that your spiral doesn't get like ridiculously big, for example. Or you can make sure that the velocity, because you know that you're optimizing a velocity, stays below a certain safety limit if you're doing human-robot interaction. And that becomes, and you can certify that, of course, because the program that actually runs on the robot is still just like before. Only its parameters have changed. And bounded. The change is also bounded. And yeah, it's possible to get that through the approval pipelines at large companies.
Okay. Thank you. One more. Okay, so one last question and then we have a break.
Yeah, thanks for the awesome talk. Question from VR demonstration. So basically you segment the human doing some actions in VR, right? Do you have, and then you briefly mentioned about intentions learning from this kind of episodes, right? Do you use some techniques to derive those intentions, or the event segmentations is basically the intentions grounding from the human demonstrations?
It is actually the latter. And this is a thing that we want to improve in the future. So maybe you see here that this is segmented using force dynamic events. And whenever the set of force dynamic events that currently hold changes, we infer a new anonymous action, which we don't know yet what it is because we infer that later. But and that's really suboptimal because sometimes there are glitches in the VR environment where contacts are briefly sort of suspended even though the objects are still in contact. So these kinds of things, or the human does, at some point the human maybe dropped the thing and picked it up again, and this was a human error. But this generates a completely different timeline here. And that's a thing where, yes, I would love to pull the semantic interpretation much, much higher, right? And say, okay, we want actually not to really be considered about force dynamic events here, but rather about other things. But I am not sure yet what these things are, and I would love to do more research in that direction.
Thanks.
Thank you very much for this exciting talk. Now we have a break. Thank you for joining, and it would be nice to have you here again.
Thank you.